Hello there. In this tutorial, well, it's not going to be a tutorial per se, it's going to be a show and tell. Basically, I'm going to take a look at the design and modeling process of a robot arm. I'm not going to model the robot from scratch, this robot arm from scratch, that's your job, but I'm going to give you a couple of pointers and tips and tricks about getting this done. So this is the kind of a robot arm that we are talking about. This is a pretty standard industrial grade robot arm designed for, let's say, doing various tasks in a factory environment, such as picking up objects, placing them somewhere, the kind of task that we want our robot to do, or welding, spraying paint, whatever. This is pretty standard stuff by now. In any case, you have seen these robots or similar robots many times. There's freely available information, freely available videos and pictures out there, so you can get a pretty good idea of what a robot arm looks like. And we're going to do something similar. Now, it doesn't have to be super exact. You can come up with your own details. Obviously, you're going to adjust the size of this thing to fit your scene in particular, because remember, you have a door animation, a cart that goes through that door, and then there's going to be an object in that cart which you will have to pick up. So chances are your robot will have to be bigger than the cart and the door, because that way you can actually pick up an object and place it somewhere that you're going to set up in your animation. Okay, so what I have here is a robot arm with multiple degrees of freedom, which means that every single one of these joints articulate in a certain axis, but together they can perform complicated tasks on multiple degrees of freedom, like X, Y, and Z axis, when these pieces are combined together, are achievable. So let's start from the beginning. What is this robot? How does it move? So it has a base. This is the robot arm base. Now I'm going to take everything out of this system. Right now they are in a hierarchy. As you can see, I'm going to take everything out, and I have a locator here, and this locator is just for convenience. You don't have to use the locator. I kind of like the locator because that way, if I want to create a duplicate of this system, let me show you what I mean. So let me put everything back. Right now everything is under this locator, and if I duplicate this, okay, the locator name will be incrementally increased. So this was robot arm 1, this became robot arm 2, obviously, but the naming standards inside the locator didn't change, because these are the sub objects of that locator object. Okay, so this is why I didn't want to change the name. Otherwise, this is why I didn't want this thing to stay out, because the name would change. So robot arm base 2 will be the parent object. I didn't want that, so I put them inside a locator. You don't have to. If you want, you can. Okay, so let's delete robot arm 2. We don't need it, and let's take everything out. Okay, so locator object, it's in the origin point, as you can see, 0, 0, 0, x0, y0, z0, and base is also in the origin. As you can see, it doesn't have a bottom because no need. You're going to place it on a ground anyway. We're never going to see the bottom side of this thing, so I didn't bother modeling it. And this is going to be the fixed portion of our model, fixed portion of this robot. We're going to place it somewhere and it's going to stay there. It is not going to be animated. That's the intention anyway. And then we have the turntable. Now we get into the degrees of freedom. This turntable, as you can understand from its pretty simple mechanics, only rotates around y-axis. Above that is the big arm. Now big arm only rotates in z-axis. Obviously z or x will depend on how you construct your model. I mean, I could have just as easily put this 90 degrees and put that 90 degrees, and there you go. Now this only rotates in x direction, on the x-axis, and not the z-axis. So it will depend on that, obviously, but it is going to still have 1 degree of freedom, or one axis to rotate in. Okay, to rotate on, sorry. And then we have the small arm, similar story here, it only rotates on z-axis. And then we have this claw base. Claw base also rotates only on z-axis. And then we have the claw turntable, which rotates only on y-axis. So we can adjust the hands, the claws of this actual robot. Now, this system might be different from any type of reference material you find, because, for example, if you look at this robot example from KUKA, you'll see that at the end of the small arm, there is a portion that is able to rotate around y-axis, and then comes the articulated hand or claw, or this tip of the robot, the business end, let's say, of the robot articulates on a z-axis. So you can switch those axes manually when you're designing. It doesn't have to be one specific thing. I decided to do it this way. Maybe KUKA's way of doing it might be the better option, because they're actually building these things for real, so they must know something. But in my example, I decided to articulate this arm as such, and meaning that this will only rotate around z-axis and this will only rotate around y-axis. And then we have two identical claw pieces on both sides of this claw turntable. I decided to call it a turntable. Okay, and they articulate on x-axis opposite the z-axis. Doesn't matter, it could have been just oriented the other way as well, and it could have been like this, and those claws might have been sticking out from here. Doesn't matter really, but again, the idea here is only one axis of rotation per joint. That's the idea. We are not using ball joints. Our skeletal structure, for example, rotates around multiple axes. So my hand articulates freely. I mean, it has its own limits, obviously. I can only articulate it so much, okay? It won't go anywhere. And this kind of a rotation is not, my hand rotation is actually not coming from my wrist, but actually from my elbow, because I have double skeletons here, double bones here, and that those, what do you call them, clavicles, I believe, or maybe I might be mistaken. I'm not fond of anatomy. In any case, those types of articulations in an organic model, a human being or an animal, is different. Those are ball joints. These are not ball joints. These are effectively hinges. They only rotate around the single axis. That's how they produce power. That's how they produce torque. Basically, these are placeholder objects. Obviously, they are not detailed in any way. This is not a game-ready model or anything. It is just something that will give us this relative size and shape of this system in a gaming environment, similar to your door, similar to your car. They're not super detailed, and they don't have to be, but you can still read the intentions behind the mechanical details here. For example, this is probably a large servo motor, and so is this, and in here somewhere there's another servo motor perhaps. In any case, this is a sound, let's say, believable, legitimate mechanical suggestion. Okay, so I ask you to do the same thing. You can keep it even simpler than this. You can just go ahead and, I don't know, let's say, model an arm such as this. And obviously, don't do this, don't go this fast, because you will have to still use the grid. That is a pretty important part of this type of setup. So this is an arm, right? We understand its articulation point, we understand the joint in question, and then it has an arm, and probably something will also stick out of this end. So do something like this, but do it more clearly with accurate dimensions, because dimensions once again matters in animation. So when you look at the side view, for example, obviously this is the front view, but you get the idea. And one of the side views of this model system, you'll see that my articulation points, my joint points, are directly on the grid. This is going to help me a lot because I can now control the animation precisely. I know exactly how much of a reach this thing has. And once again, these larger squares with the darker gray lines, they are 1 meter because I have set up my grid options as such. Grid lines are every 100 units. A unit in Maya is a centimeter, so this makes all of these larger grids, grid lines and numbers, dark gray, as you can see. Those are meters, and I subdivide that meter into 10 equal chunks. That gives me 10 centimeters. Okay, so this way I can, even when I'm outside of a modeling system that resides in another file somewhere, and that is the case right now. My door system and my cart is somewhere else. I know their dimensions. I am aware of the system that they are designed for, and that is the metric system. Okay, this is somewhat semi-realistic, let's say. Because of that, I can just easily design this kind of a robot and say, okay, like this thing has 1, 2, 3, 4, 5, 6, 6-ish, 6.5-ish meter of reach. Maybe if you exclude the turntable, obviously 6 meters is the most it can reach. So that is more than enough for me to pick up an object from my cart, because my cart was approximately 1.5 meters wide, 1.5 meters long, and like 70 or 80 centimeters wide, if I remember correctly. So that way I can easily pick up an object from it. That's why we use the grid. That's why we use accurate dimensions, and we snap everything. Speaking of snaps, take a look at the joints. Take a look at the pivot points and the location of the pivot points on the joints. So this thing is the base, so its position, its pivot position is on the being on the origin makes sense, because we're going to place it somewhere, or we're going to place it inside the locator and place the locator somewhere, and it's going to stay there. It's not going to change any positions. It's not going to be animated. But when we look at the turntable, now we intend to rotate this turntable, so its pivot position has to be exactly on the center of the rotation, okay, of this mechanical rotation, because we are going to imitate that mechanical aspect of this robot, like we did everything, like we did with everything from the door animation to cart animation, okay, and it's on the origin as well. I'm right in the middle, okay. If you look at the big arm, big arm's rotation axis, remember, was Z. So this yellow line is going to be my rotation, okay? And I can basically, as long as this thing stays on that line, I can place it anywhere, okay? As long as it stays on this line, I can move it as such. Doesn't matter, because I'm only going to rotate it on that axis, and if the position of that axis doesn't change, then I'm happy with it. But for ease of reference, I'm just placing it, instead of placing it on the front of this object, which is obviously something you can do. Instead of doing that, I'm just placing it inside the middle of the object, so it aligns with the rest of the system. Okay, because the rest of the system, as you can see, is in a T-pose. That's one of the other things that you should be considerate about. So, for example, common sense, or at least, well, for the first time you're doing this, trying to imagine the robot in movement, as it's articulating, might be a tempting idea. So you might want to set your robot up something like this, like half moving, right? You might wanting to do something like this, model something like this, but that's not the best idea, because then your rotations, when you freeze them, they will be zeroed out, and then you won't be able to figure out how much of a rotational coverage that you're allowed to make in this kind of a mechanical suggestion. Because let me put these together and show you what I mean. The reason why we are putting these pivots on the center, and the reason why this is modeled in a T-pose kind of setup, is that when you put everything together, let's put everything together. Let's do something like this, just do this. Okay, so now everything is nested inside each other as it should be. So when I animate this, or if I model this, sorry, like so, and then freeze all of these transformations, okay, first of all it might start breaking apart, but let's say that this is frozen, and now this is frozen, and this is frozen, and this is frozen, and everything is frozen, so everything is zeroed out. Now here we have a problem, because as you can see, this thing is unable to rotate freely for 360 degrees. Okay, it has to stop somewhere, otherwise it is going to collide with itself, or another part of this object would collide with itself, collide with the rest of the model. So we have to limit this. We will have to limit this object's rotation as we are animating it. And in order to figure out those rotational limits, we have to put it in a position that will give us a neutral zone. And that neutral zone is the T-pose. That's why humanoid characters, for example, are modeled in T-pose. So human model T-pose, let's say. This is the T-pose. You have seen this before. Because if you model your arms in another position, then it will be harder to animate them and set up these rotational dependencies and limits in the joints later. So that's why this is the neutral position of a character, and for a robot arm, I believe this is a good place to begin, because everything is in line, every pivot point is in line. We figure out, we understand the rotational limits that is available for this particular model, and we apply them, and then we can start posing this thing, or we can start animating this thing. And that's why, back to the beginning, all of these pivot points are exactly on the origin, at least in terms of X and Z. Okay, on terms of X and Z, and also Y, they're on the origin. When you're looking at them from above, I mean, they are not on the origin on the y-axis because we are reaching upwards, but you get the idea. Okay, so that's how this system is set up. Obviously, the claw fingers, let's say, these claw fingers or pivot points are not aligned to the middle of this object or to the origin point when you're looking from above, because otherwise the rotation would be weird. But the rest of the system, as long as we can stay on the origin, we are staying on the origin, and that will give us a better idea of what's going on. It's easier to understand because we're not going to just leave it with modeling this object. We're going to create some controllers for it. And when we are creating the controllers, we're going to then discard this object. We're going to make it unselectable and then animate it. So until that time, we have to be placing our pivot points and snapping them to the exact middles of these, let's say, hinges or joints appropriately. So, for example, if you're creating a cylinder and if that cylinder's center point is not on the grid, you will have to at least snap this pivot to the middle vertex of that cylindrical shape. You have to adjust your pivot points correctly, because if, for example, if you're not using the grid and the pivot position is located incorrectly, then this rotation will look weird, as you can see. right? So that's the idea. Use the grid to your advantage. I mean, grid is your friend. Grid is not a chore. Grid is not something that you should stay away from. Quite the contrary, you should use it as much as possible. And finally, we have the arrangement. We have the parent-child relationship here, and that is also something you will need to create. We need to create, first of all, different pieces and then nest those pieces inside each other. Name your objects accordingly. Make sure after you set up their positions, let me take out everything again. After you set up your objects, okay, like those positions and locations and rotations are all correct, and there might be some numbers around here that you might have translated this object on X, rotated it on Z, whatever, but you're happy with its location, everything fits other stuff perfectly, then you will have to freeze the transformation. Don't forget to freeze the transformation. You go to modify, freeze transformation, and delete the history as well. You go to edit, delete by type, history. Okay, that is going to delete all of the construction history, modifier history of that particular selected object. And if you want to delete all types of history in the scene, you can just select delete all by type history. So when you do that, this channel box will be empty, translates will be all 0, rotates will be all 0, scales will be all 1, and there's not going to be a modifier. You name your robot pieces meaningfully so that you can track what these objects are. That is a big part of this the animation, right? And all kinds of animation modeling for animation tasks. And then you make sure everything is in order, all of the pivot points are set up correctly. Then you start nesting them, starting with the base and the turntable above it. I mean, obviously, if you want to put other objects or other kinds of joints in the middle, or you want to do a robot with 3 arms and not just 2, big arm, middle arm, small arm, that's perfectly viable. Maybe you want to put just 1 turntable and not 2, okay? Or maybe you want to use 3 turntables. Do whatever you wish, okay? Big arm. Sorry, I put the small arm first. So small arm inside big arm, and then claw base, and then claw turntable, and then the fingers. And that's about it. This is how the parent and child relationship, the object hierarchy, will be set up in the outliner. So, and your model will be ready, and we'll be doing the animation next week. Hope this helps. You can use Blender, you can use Maya, whatever you feel comfortable with, use it, but make sure the model is good, model is ready to go, and if there are any problems with it, fix it in Maya. Make sure everything fits together in Maya. Doesn't matter if you have done it in Blender, and I'll see you next week. Bye.